In this video lecture, I will explain push-down automata, or we also call it PDA. So here PDA stands for push-down automata. Okay, so till now we have seen a context-free language can be described using context-free grammar. So we have context-free language and it can be described using context-free grammar. Okay, but we have not encountered an automata to recognize the context-free language, as we had finite automata to recognize the regular language. So for regular language, we had finite automata and finite automata like DFA or NFA. So for finite automata, we have seen DFA, NFA or null NFA. Okay, so this finite automata is automata for regular language, but this finite automata is not powerful enough to recognize many context-free language. So since the finite automata have strict finite memory, it is not possible to construct those machines to accept the context-free language. So the automata to recognize CFL, it may require some additional amount of storage, which will be used to store the data. For example, if I take the example of parenthesis matching, okay, if I take parenthesis matching. So in parenthesis matching, we will be having left and right parenthesis, right? We'll be having left and right parenthesis. So if we encounter left parenthesis, we say when left parenthesis is encountered, it is required to store the left parenthesis. So what we will be doing? We will be storing it onto the stack. Okay, so left parenthesis means we will push it onto the stack. Okay, we will push it onto the stack. And when we encounter right parenthesis, what we do? That means this one. When we encounter left, we push it onto the stack. And when we encounter right parenthesis, we may have to pop the corresponding left parenthesis from the stack. So now what we will be doing? We will be performing pop operation. So whatever is there in the stack, from the top of the stack, we will be popping. So for left parenthesis, we are going to push it onto the stack, and when we encounter right parenthesis, we are going to pop the corresponding left parenthesis from the stack. So thus stack is used to remember the scanned symbol. Okay, so this is evident that if we design the automata to accept CFL, and sometimes it is required to count the symbols also. For example, if I say we have a power n, b power n, this is the language, and where n is greater than and equal to 0. So after reading n number of a's, what we should see? We should see that n number of b's exist, because it is same number of a followed by same number of b. So after number of a, n number of a, we have to check the same number of b's also exist. So the automata that we construct to accept this CFL, it should be in a position to count. At the same time, it should have sufficient memory also to hold the string scanned. So since DFA and NFA cannot count and cannot store the input for future reference, okay, so that is the limitation of finite automata. So DFA and NFA, they cannot count as well as store the input for future reference. So that is the limitation of finite automata. So that's why we will go with the push down automata. So we are forced, so that way we are forced to have a new machine that is called as push down automata, PDA. Okay, and now the PDA, we will say it is NFA with the exception that PDA has the extra stack. So NFA plus stack will be there. Okay, so the definition of PDA is similar to the definition of NFA with a slight change. Okay, now how the transition will be for PDA. Now if I say NFA, right? NFA or DFA. So transition function delta will be what? There will be two parameters, the current state of the machine, and then we write the input alphabet, and then the output will be the next state of the machine. So this will be the transition function for finite automata. And if it is NFA, so here I will be having, this will be a subset of 2 to the power q. So here we will be getting subset of 2 to the power q. Even null transition is also fine for NFA. Now, so here the transition, how we will define the transition here. Let us not worry about how to get these transition at this point of time. That I will be discussing later on. So assume that Q0 is the start state. Q0 is the start state. Okay. And there is initial Z0 symbol. Z0 we will say the initial symbol on the stack, indicating the stack is empty. Okay. Now, since there is a null transition, the PDA is actually non-deterministic. So there will be null transition also. So we will say PDA is non-deterministic, and in a non-deterministic PDA there will be null transition, or there may be multiple transition from the same state on a given input, like NFA. The difference between DFA and NFA is that only. If I say DFA, so for a given, from any state for a given input there will be a single state, but in case of NFA there will be set of states. So when we are saying PDA is a NFA plus stack, so the same thing applies here also. It will be having null transition, or there may be a multiple transition from the same state on a given input. So if I give some input, there can be more than one state here when specified symbol is there on the stack. Now how the transition will look like for PDA? Here we'll be writing the current state of the machine, and this first parameter is the current state, second parameter is the input alphabet, and then this is the stack top. So initially Z0 will be there in the stack because this is the initial symbol on the stack, and then here we will be getting the next state of the machine, and this will be the stack content. This is the stack content. Okay, so here this means the machine is in state Q0, we are giving input A, and the stack top is Z0. The machine remains in the same state and we are pushing A onto the stack. So A Z0, that means A is pushed onto the stack. Z0 was already there. After reading A, we are going to push A onto the stack. So this indicates the push operation. Now if I say Q0 B Z0, so this means the current state of the machine is Q0, the input symbol is B, and the stack top is Z0, and machine remains in the same state Q0, and B Z0 means we are going to push B onto the stack. Same way, if I say Q0 AA, so that means the input is A, the stack top is also A, and then we are saying Q0 means the state is Q0 only, machine remains in the same state, and we are going to push A onto the stack. So A was there on the top, we are going to push A only, so the stack content will be AA. And then if I say, suppose if I say delta Q0 C Z0. So the machine is in state Q0, we are giving input C, Z0 is there on the stack top, and then we are saying we are going to change the state from Q0 to Q1, and Z0 is there in the stack, means we are not going to perform any push or pop operation. So these three you can say is the example of push operation. So how we perform push operation, and this is do nothing. So we are not going to perform push or pop. We are just reading the input C, stack top is Z0, and we are not going to do anything. That Z0 will be there in the stack, and no pushing or popping operation. Okay. Now if I say delta, if I say Q1 is the state, I give input A, stack top is also A, and then machine remains in the same state Q1 and epsilon. So this indicate pop operation. So whatever is there in the top, that will be popped out. So we are reading A, top of the stack is also A, and when we are writing epsilon, that means the top, whatever is there on the top of the stack will be popped out. So these three operations will be there in PDA. This is how we will show the transition. Okay. So now so with this, how will we define the transition function? So here you can see this first parameter is nothing but, so this first parameter is going to come from set of state capital Q, and the second parameter is the input alphabet. So this will be sigma, and even I can have null here. So this will be sigma union epsilon, and then this will be the third parameter of the transition function will be the stack content. So this is the symbol we will be using to represent the stack content, and here I am going to get again some state. So it will come from set of state capital Q, and this will be the stack content. So we will be using this symbol and star because this represent the stack content and this represent the stack top. Okay, so this will be the transition function. So now unless otherwise specified, let us call this PDA as non-deterministic PDA, and the formal definition of PDA will be, we will be having like for DFA we had 5 tuple. So here we will be having Q as finite automata, that will be set of state, sigma will be the input alphabet, and this symbol is used to represent the stack content, delta is a transition function, Q naught is the start state, and Z naught is the initial stack symbol, and F is the final state.